Hello, good evening, friends, and welcome to another session of ESSEC Colloquium here. We are lucky here to have Professor Miron Livny, a very eminent person in throughput computing and physical science, and it is going to be a very interesting lecture. I request Bridge to give a proper introduction to speaker.
Thank you. Thank you for organizing this. It's my great pleasure to be here in introducing our speaker today, estimable colleagues and friends. If computers had a Hall of Fame, I'm sure Miron would be inducted several times in it. And so please join me in welcoming Professor Miron Livny. Now, Miron's career could fill the memory of a supercomputer very easily. Thankfully for us, I only have 3 minutes to cover his accomplishments. As the John P. Morgridge Professor of Computer Science at the University of Wisconsin-Madison and the founding director of the Center for High Throughput Computing, Miron had become synonymous with distributed computing. In fact, his pioneering work in high throughput computing is so impactful that if you have ever submitted a job to a computing grid, chances are you have benefited from his contributions. Some might even say he has helped finish more jobs on time than coffee and deadlines combined. Miron's groundbreaking journey began early when he had a radical idea that computers shouldn't be just sitting idle. His 1983 PhD thesis titled Load Balancing in Homogeneous Distributed Systems was one of the first to explore how computers in a network could share their workloads, creating a kind of computational symphony. From his work, he birthed the concept of high throughput computing, a system that has forever changed the landscape of scientific discovery. And Miron has turned the notion of waiting for your turn into let all get this done together. His first major publication, which stemmed from his PhD research, laid the foundation for distributed computing system and inspired generations of students, scientists, and researchers to follow in his footsteps. It's safe to say that Miron transformed the inefficiency of idle computers into an opportunity to push the boundaries of the science. Speaking of students, Miron has mentored a staggering number, many of whom have gone on to make significant contributions in academia and industry. His legacy isn't just in the software and systems he built, but in the talented minds he has shaped. One of his major accomplishments in the creation of the ST Condor software suite, this software presented ideas for batch systems which have been picked up by almost every other batch system you might have used in your life. And let's be clear, it's not just a cool name that helps researchers all over the world make sense of the vast amounts of data by distributing computational tasks across a network of computers. It's why computational problems that could take years are now solved in weeks. In fact, even when Google was cooking up its baseline infrastructure for processing vast amount of workloads, they were reading the recipes from Miron's cookbook. In addition to his numerous achievements, Miron serves as the Chief Technology Officer at the Wisconsin Institute for Discovery and as the Technical Director of the Open Science Grid. Honestly, if we were to list all of his titles, we might still be here tomorrow. But suffice it to say, if there is a computing grid, cluster, or a network, chances are Miron has figured it out all and optimized it. Beyond the technical brilliance, Miron is also known for his collaborative spirit. He has built frameworks that enable scientists to work together, harnessing the power of distributed infrastructures to revolutionize scientific discovery through computation. So, whatever you are here for, the science, the breakthroughs, or just to marvel at how one man can hold so many titles and make it look all easy, you are in for a treat. Please join me in welcoming Professor Miron Livny, the trailblazer of the high throughput computing.
For this amazing introduction. I think that if I knew that there would be an introduction like this, I would have skipped almost all my slides because some of them will provide a repeat. So thank you for joining us this afternoon, and I don't see here many faces from the previous presentation that I gave standing here earlier this week. So I hope there's not too much of a repeat here. And also, please don't hesitate to chime in, ask questions, voice your concerns as I present. If you want me to talk more about something, I'll be happy. There's no need to cover all the slides. So let's get going. And I picked this title and the abstract, knowing that here TIFR, it is an organization in the physical sciences. So I tried to focus the examples and the lessons on the physics side. And as you may have learned from my previous presentation, I always like to think back and to look back into history and what happened and how it happened as a guide to help us move forward and not to spend the time speculating on what will happen in the future. So maybe to set the stage, here is one example of a long-standing joint activity that we have with the gravitational wave community that started with LIGO in the US, I would say at least 2 decades ago. And here's today IGWIN, which is the International Gravitational Wave Network that is going to soon have also an Indian component in it. Here's one of the web pages describing how IGWIN is, how to use it with Condor. And I just picked up earlier this morning 2 weekly reports to give you a feeling of what's cooking just on IGWIN. It's not the entire computing infrastructure, just the distributed one. And these are 2 weekly reports. And you see it, 1 week it was 300,000, the other one it was close to 500,000 jobs that executed on the IGWIN. So that gives you sort of a feeling of the kind of stuff that we are dealing with when we talk about this kind of computing. And yeah. Excuse me? Yeah. Yeah, good CPU hours. So we like to collect also something that we call good put, which is not well defined, and therefore I don't. It's sort of an indicator. So if capacity doesn't make it to a successful completion, or the job has been removed, we at the moment don't count it as good put, we count it as bad put. So it is not CPU utilization but it is an indicator. If there are a lot of jobs removed, it's a reason for us to look around and understand what is happening. Or if, because of the opportunistic nature of the resources, if a lot of them have to be restarted and re-executed. So it's sort of a smell test of and actually I gave you the total. We get the report. I'll be happy to show you that on offline per user. So some of them may be in the 90, 100, and somebody may be in the 10 because they removed all their jobs after a while. And so that's, and thank you for asking and paying attention.
This is by the user or the user? The jobs removed by the user?
Yeah.
Or the citizen?
No, by the user. That is, we can get into some of the more philosophical question of how people are using capacity. So we have cases where I saw low goods put because a lot was removed, and they say, okay, we run it. It may even exit successful completion is also an art by itself. How do you know that the job exited successfully? So, and researchers are not doing a great job with exit codes. So we, if it's non-zero, we consider it as bad put because so that's the reason why I say it's not an exact science, but it's more of should we talk to this user? What's happening? Oh, some of them are running it and they don't ever expect it to converge, but they will say run it until as long as you can, and I will take the result at the end rather than stop running. It's when you move from our experience outside organized experiments to more generic researcher coming in and doing whatever they feel is best for their science, you get various behaviors of the jobs. And both of your questions are indicators that monitoring environment like this is extremely difficult. And we are investing quite a bit in figuring out what is the best information we can get out of it in order to help the whole ecosystem to use the capacity in a better way to advance the science. I have to learn how to do it right. Okay, so in addition to Igwin, that is somewhere here, and again, don't take any of these numbers to the bank. It is what we are able to collect, and some of the jobs are the real jobs. Some of them are what we call the glide-ins, which are the containers of the payload. But I wanted to give you sort of a feeling of these are all physics collaborations that we have been working with them in different ways. And the important thing also is to see that they are of different sizes. And I think it's also important to keep in mind that the impact on science is not necessarily by the size of the collaboration, but can you help a collaboration to go to the next level? And that's part of the message that I want to leave with you here at the IFR is that there are opportunities to do better at different scales. And it's important as we are moving forward to think about the different scales. It's not only CMS that is the largest distributed pool that we have, which is in the 400,000 core range, but if it's GlueX, which is only 1,000, and so you have them all over. So in '96, I coined the term high throughput computing. It was first in a presentation at NASA, and then shortly after that at the presentation at CERN. So in a way to show you that quite a bit of our roots are in the, if you want, the HAP community, or the particle physics community. So that's when I differentiated between what was out there, the high performance, and what we believe is a different way of computing, which is the throughput computing, and was interviewed by H.C. Guaya. And I'm not going to spend too much time about comparing between the two. It became quite a discussion at a presentation I gave yesterday at the IIT, but I'm happy to go in this direction if that's where you will take here. But my collaboration with the HAP community started with an email from René van Danzig from NICAF in the Netherlands that came across the paper that was mentioned, and I'll have a slide about it in a moment, that we published a year before that. And he basically said, we would like to have this functionality, and we figured out you guys did it, so why should we do it? And let's work on it together. And this is the original paper that we published about the Condor system in '88. And you can see that from the beginning, we focused on working with users and figuring out how it works in a real environment. And I will revisit this concept in a few slides. But it was not here's some kind of an idea of doing things, but it was more here's a deployed system on workstation at the University of Wisconsin, and this is what we have observed, and this is the real software behind it. So actually the conference where this was published selected this one out of two papers as what's the test of time after 40 years. The conference has been now running for 40 years, and they said which one were the two most influential papers, and that was one of them. So René and a student of his started to look into this idea in the early 90s of putting together what we call Condor flocking, which is actually going beyond a single Condor system and bringing together several Condor systems as a way to move forward. And we actually deployed the first prototype in '93 and start running it in '94. And we had a worldwide flock of Condors actually operating in the mid-90s. And it went all the way from Dubna in Russia via a satellite link to Berlin, because at the time Dubna had only a phone line to Moscow. And then into the Amsterdam area, which included NICAF, and we had some stuff at CERN and all the way to Wisconsin. And you can see the numbers then. They were impressive for the time, but the idea was already there, and we used it to do already science. So the easy application was simulated annealing, which is a perfect match for such an environment. But we also had a giant, before it had even numbers, a simulation that started in Dubna and ended up in Wisconsin through this infrastructure. All these ideas triggered the presentation that I gave at CERN in '92, for a vision of a worldwide computing environment that consists of flocks of condors. And that, again, was early. And in 94, 95, we had the first implementation of it. And it took about 20 plus years for this idea to actually being sort of adopted by the community as a production one. Following the presentation at CERN in the mid-90s, I was approached by Paolo Massanti from INFN, and we started an effort throughout Italy, and we ended up with a condor pool throughout the INFN system that is depicted here with all the checkpointing opportunities. And it's always nice to look back and to see this is the way it looked. And we talked earlier about open source and standard. You see here already, there were all these different flavors of Unix. And the software was with a lot of work to make sure that it runs on all this. And including, we have a stable and a pretty widely used version on Windows that is more in the commercial side of the house than the research side, which is mainly Unix. So we were very proud that we had 200 CPUs at the time. And here is, again, for an organization like TIFR, here are all the type of science that can benefit from this infrastructure. It's not only Monte Carlo simulation. And having the capacity readily available for all these different science activities was useful. And these are the number of hours we did in a year, about 38 years. So it was out of these 200, you know, if they were completely used by us, it would have been 200 years. And so we did 40 years, which is about a fifth of their capacity was used by this Condor system. Gives you a feeling of how it all works. So fast forward 2006, I established the Center for High Throughput Computing in Wisconsin, and it was and is structured on the foundation of what we call translational computer science. And the idea here is that in the translational process, you are moving ideas into the different scientific domains, and then you learn from that and bring it back to the laboratory to do new, different, better stuff, and then you push it back. But the pushing goes through two steps. One is you have to turn your ideas into something that can be deployed, and you learn from the deployment, because deploying some of this stuff is non-trivial, and there is a need for quite a bit of innovation just to get the deployment going. And the deployment includes the maintenance and monitoring and all the good stuff. And then can you build a community of researchers that will actually use it? And in all these cases, you need the feedback into the laboratory. So this is the methodology that we have been following from the very beginning. I showed you the original paper in the 80s, that there was always deploy it for real, build a community of users, and continuously learn from what you experience in order to improve what is in the laboratory. So that's something that I want you to always keep in mind. if and when you are dealing with us, that's the way we operate. So we are not a vendor that we say this is the way it is. We actually want to hear about what is not working, because that's the only way that we can do better. Because if everything is fine, then we become useless. So this methodology works and is recognized, as you heard in the amazing introduction that we had to the Hall of Fame in distributed computing. That was recognized by the IEEE, which is my domain science, about the contribution of what we are doing, which is, again, a litmus test on, does this thing work? And it definitely does. It's not easy, it's not simple, but it does work. Part of what we do is to run all these services on our campus. So to give you a feeling, and again, as a message to TIFR, as an organization, you can look at it as a campus, like our campus. Now, our campus has a research budget, not including everything we do in education and all this, just what's called research expenditure of 1.3, or just the other day I heard $1.5 billion a year. So it's a pretty significant science operation. And we deploy services for this organization as part of the CHTC. So here are some numbers. We have been working with over 300 projects. We have delivered about 35,000 core years per year. So this gives you a feeling that it's about 40,000 cores, you know, with some of the waste of not, and that is delivered, not potential can or whatever. And you can see also about our style, we don't talk about the capacity we have. We talk about what we actually were able to deliver, because that's what matters. We also run a Slurm cluster. So between, when I gave you the 40, it is about the sum of the HTC and the HPC part. And an important element in all this, which is, again, a talk by itself, is the whole idea of research computing facilitation that we pioneered in the CHTC. And we had about 1,000 interaction of the facilitators, which is about, if you have 250 working days a year, it's about 4 interaction per day. So getting people to benefit from what you have requires facilitation. And here you can see the different colleges, and some of them are not physical sciences, obviously. So CHTC is a home for 2 software stacked, if you want. Yes.
Side, I would like to ask, like, in the hardware side, is there any plot or any chart you have made to see how many, or is the typical wait time for a job to be executed? Like, you have some 34K computing hours, right? Some 40,000 cores you have. So what I'm asking is, how much is the typical wait time for the jobs? How long is the job waiting to be executed in a queue? And is that time increasing?
We don't keep track of this, because in an HTC environment, it's meaningless.
But how do you know that it is sufficient? Like,
the question of how do you define sufficient I think is problematic because let me take a HAP experiment as an example. The more simulated data you have, the better is your statistics. So it's never sufficient. So if you have a 1-to-1 ratio between measured and simulated, it's not as good as having 2-to-1 or 3-to-1 or 4-to-1 or 5. You know, I can spend the next 25 minutes just going up one step at a time. So the philosophy is of a throughput computing system, and I can show you the number of jobs. We have people who submit for let's say 100,000 jobs in one go. They are going to wait. So how long is the waiting time? Eventually they will come out. We are much more concerned in our work on statistics like human intervention, because we are trying to optimize the time that individuals have to spend babysitting their hardware, their computer, and then. So at the end of the day, we talk to our researchers and we try to understand how their science is going. And a good throughput computing researcher always has jobs in the queue, because you never know when the capacity will show up. So if I catch you with an empty queue, you screwed up. So you have to change your mindset from looking at queuing time to productivity, and that is part of the story of throughput. It is not how long did you wait, but how many jobs did you produce in a week. If you are coming with a single job and you want to get it out quickly, which is an HPC mentality, I mean, we can do things. We can give you priority. We can get you through the, but that's not what I think the value that this approach brings to science. Okay, and I can tell you, which is I have been talking to researchers that work sequentially. So let's get one parameter down and look at it and decide the next parameter next. And I say, you're better off run a list of jobs, what I call, on a whole bunch of parameters, get a feeling for what's happening. You may have to wait longer, but you have much more, and maybe your entire workload will end up sooner because you don't go sequentially, but you scale out.
Because number of jobs we typically submit is tremendously increasing as our runs are increasing. So the number of jobs that HT condo,
yes,
that is tremendously increasing with time. So now the question comes is the sustainability. Like by what time it will be in a situation that you have to wait much longer to get the jobs done. So that's the question I was trying to get through, but we'll discuss it later.
yeah, okay. That is we can talk about it. Look, I usually, when I work with a researcher, I look at what is your workflow of the science. So the question is, how can computing get you do more science? And maybe what we do is not, it's not going to help you. You know, if you come in and you say, my science depends on, I need now access to 100,000 cores for 10 hours now, I said, go somewhere else. Which is another important part of the whole dialogue. It doesn't make sense to bring you in with a sort of an illusion that we can, it's better that we say no. Okay. Yes, go ahead.
There's a lot of details here. So, for example, it's a huge setup with a lot of heterogeneous applications.
Yeah.
So you must have had lots of challenges integrating the hardware. Because there are different types of hardware, for example, and you have to match that to the needs of the researcher.
Mm-hmm.
So, you have any thoughts about how do you discuss this with the researchers and how do you came up to integrate all this into one framework?
So the situation on the campus is even more complicated than is captured here, because the hardware that is captured here doesn't include hardware that is owned by other parts on the campus and is still accessible in a sharing environment. So we have a CMS tier 2. These numbers are not here. We have IceCube. The numbers are not here. So the philosophy of Condor, or of, I would say, of distributed system, which is a topic by itself, is to allow local autonomy. At the same time, we also are inherently heterogeneous. So our software, I showed you, if even in the INFN class, we were running on HPUX and this and this and this and that. So we are continuously accommodating heterogeneity. And things are tricky also. What is your funding sources? Some of it you buy as part of your grant, and some of it is the university is providing, and some of this is that. So it is a live process where the key is that the software and the philosophy is based on what I said: local autonomy and heterogeneity. So you can tell us, the scheduler or the resource allocation mechanism, everything you want about your piece of hardware. Okay? And we can take it into account. So if you tell me in which floor you are sitting, and assuming that lower floors have less neutrinos and being hit by less neutrinos, and you want to run only on those that are in the lower floor, we can accommodate it. If you are telling us which floor it is, you can tell me don't run on higher floors. And I don't want to get into all these details because we have hundreds and hundreds of man pages. You can imagine that over the 40 years, a lot of features came in, but the underpinning philosophy, which is distributed computing, has been local autonomy and heterogeneity. And we also buy our hardware heterogeneity. We never go after big purchases of the same thing.
One big place for school of computers is to distribute across all the campus.
This is distributed across several sites. What I just, actually, some of it is hosted outside of the campus because it's sitting at the hosting service, because we don't have room for everything on the campus, but we don't care. But we know that it's there versus it's here, in the same way that if tomorrow morning I put a computer here at TIFR, I can make it part of our system and I will know it's a TIFR. Okay, so it's a different mindset of going out there and buying one a homogeneous machine, which is the mentality of HPC, because if you're running an MPI job across heterogeneous servers, then you're doomed. Okay? But you are also stuck with whatever you invested today for the next, whatever, 5, 6, 8 years. Because, yeah. And we are coming and saying, buy 2 machines today and 2 machines tomorrow and 2 machines the day after that. And you are better off keeping the money in the bank rather than putting unused capacity in the machine room. Okay, so that's the okay, good. I love this discussion, so it's don't hesitate to ask more. So as much as you don't want to talk about the software, but the software is what enables the whole damn thing. Okay? Yeah. Look, let me tell you another philosophical thing about the way that we operate. To what is called research computing, or in the US called the cyber infrastructure, consists of 3 main components: people, software, and hardware. The most difficult part is people. The second is software, and the last one is hardware. Hardware is easy. And our attitude is when it comes to hardware, the problem is solved. Because it's extremely easy to turn, in our world, money to hardware. You give me 10,000 K, I can add this capacity. How much would it cost to add this feature to the software? How much would it take to bring another good FTE into the team? Sometimes it is talk to me in 10 years. So, and that is the reason why it's important to take an approach that covers all the different pieces, where the tendency is to go to the hardware because it's the sexiest and you can show people and you can brag about your MIPS. But it's easy. You take the money and give it to a vendor and you are done. Back to the software. So there are 2 elements here, and I will talk mainly about not much time left. Obviously Condor that we started, but we recently have been working on the Pelican platform, which is dealing with the federation of data. So yes, unfortunately they had to leave, but this is the deployment of the HTC, the HD Condor software suite that we know where it's being deployed around the world. So we are talking about 160 plus sites that we know of. And they are ranging from sites that have hundreds of thousands to sites that have less than 100. By the way, this is all accessible on the web, so don't, and I will obviously be happy to leave the slides here, so this is, But the idea is that it's widely adopted, and also by commercial entities, and some of them don't want to tell anyone that they're using it, and so on and so forth. So we just at the short meeting that we had before the presentation today, we heard about some company that's using it in their Kubernetes environment or whatever, that we had no clue that they are there. The other part of the house, which I encourage you to keep an eye on, is what we call the Open Science Data Federation, that is powered by Pelican, and it is a way to federate data sets. Because the challenge is, how do you bring your data to the computation, and how do you move the results of the computation to some object store to be kept? These are the way that the OSDF is working is we have a notion of origin that's being attached to the object stores, and then we have a staging capability that are being called caches that are actually deployed in the network in order to facilitate reuse of data by the computing infrastructure. So again, this can be a discussion by itself and this is a younger, much more evolving environment than what we have on the computational side. So let me skip this, because that's another discussion about when we talk about scale, that scale has many different dimensions, and it's not always the number of cores or the megabytes and how we deal with it. And overall, as a approach in everything that we do, is we try to scale out. We try to scale out in enabling scaling out, and we try to scale out by leveraging whatever is scaled out. And one example for what is out there in terms of scaling out, these are the almost 4,000 higher education organization in the US. So all of them are potential users, and all of them are potential sources of capacity. And can you leverage the scale out? You know, and unfortunately, in too many cases, we are really looking inward rather than looking outward. So the question is, can you build whatever you are doing to scale out? So that, at the core of throughput computing is that, and we talked about it, that you want to come with as much as you can, is that you have to handle workloads that have order of 100,000 jobs. At the same time, you want to figure out how do you bring researchers that have small list of jobs, but limited skill set and mentality into this environment and allow them to grow. That if they did something at level X, can you enable them to do 10X, whatever X is? So these are ongoing, and in the US, we have quite a bit of interest and activity now funded by the NSF they call it the missing millions. I mean, all those that don't benefit from the progress in research computing, and obviously reaching to all these research organization is going to be non-trivial, or is non-trivial, because we are doing some of it. So here's another example of something that we can do. The Event Horizon Telescope, another kind of community. They are excited about pictures of black holes. And they have 11 telescopes all over the globe, and they're collecting data. And they used our stuff to generate this picture. And CK, that is playing an important role in coordinating it, his word is that what we gave them had an order of magnitude impact on their ability to do the science. And in numbers, in order to do this, they use the Open Science Pool, that is one of the services that we provide, to over 6 months to do 5 million projection that consumed 20 million core hours. And CK walked in as a user to the OS pool, which is, by the way, open to any researcher in the United States to do it, and kept doing it with his collaborators until they were done. It was no allocation, no special arrangement, no nothing. They just went ahead and did it. And I checked what they did. This is already more than a year ago. Yeah, this was May 23. Yeah, so exactly a year ago that was published. And I just checked what they did in the last year. They did about 2.5 million jobs as they are continuing. Not each projection is several jobs. Several projection in a job. So what stands behind it is the OS pool. And the OS pool consists of capacity that is contributed by over 50 institutions that are spread across over 80 sites. So some institutions have more than one site that they are contributing to the OS pool. And this is all voluntary capacity that's being brought in, voluntary for various reasons and motivations. So I'm hitting the 5 o'clock.
5 more minutes and then we'll take your questions.
5 more minutes and you take question. Okay, that's what we will do. So that is another opportunity for whatever scope you want to talk about. Is how do you come together and create your own open science pool over here that you make available for the different researchers. And here is the kind of numbers of what's happening in the OS pool. So I picked August 30th because that's when I prepared this slide. And on that day, we had 830,000 jobs that consumed, it's usually an hour per job. If you look average here, it's a little bit lower than that. It depends on who is coming in. We have one big user that, group, that there is one kid there that likes to submit 3-minute job. Okay, 3-minute job. Whatever, this is biology. Looking and matching genes with bacteria, God knows what they are doing. The important thing is that it's 10 million file transfers will go to it. And it came from 58 institutions. That's one day. Again, on the web, you can go, if you think that I gave you a special day, you will see that if you look at what's happening per year, I apologize for the smaller font here. It is 190 million jobs in 1 year. And it triggered almost 5 billion file transfers. So a better way to think about what the OS pool is doing is to think about it as hertz. Job hertz and file hertz. So as we were sitting here, the OS pool was running at 6 hertz jobs. So 6 jobs completed per second, and 150 files were transferred per second. That is software. Okay. To be cynical between the source and the destination. Now, it can, the file transfers can be arbitrarily complex. It can go from what we call the access point to the execution point in any of these institutions and back. We can do transfers via HTTP. We have some of the file transfers happening via the OSDF. The OSDF at the moment may do 10% of the transfers, but maybe 60–70% of the volume. So the challenge in throughput computing is the ability to handle the volume of activities. Because if we deliver the wrong files to the job, or we don't deliver it, and all that kind of thing, that has implication on the productivity. So when we put together the software, from our perspective, a small file and a big file are the same. And if they all go between the 2 points or different points and all this, but there is quite a bit of heterogeneity in where we can fetch the data from and where we can put the data back. And Pelican is supposed to help us to do much more, and also going directly to, we have ways to go to S3 buckets, and you can see how it goes into data that is sitting in cloud object store and stuff like that. So it's pretty diverse. But what I want to stress here is the need to do this kind of dependable management, because if these things fall apart, then the whole thing grinds to a halt. And from a throughput computing perspective, that you see from an HPC system, so if the machine is down for a day or two, it's down for a day or two, and then we are back to, that doesn't change your ranking, the MIPS are there. But from a throughput computing perspective, you lost 2 days of throughput. So these numbers will go down because you lost a week of throughput. Okay, 5 minutes over. So are there any additional questions?
Take 5 minutes of questions and
Yeah, okay.
over the tea.
So this is again about data handling and transfers. So this is a federated file or storage system, right?
It's a federated data. I would have been reluctant to call it system, because like in the compute side, each of the object stores is autonomous. So the namespace of each of the object stores is autonomous, and then you create a namespace on top of it But eventually, when you come to the object store, they control it. It's not that it's not AFS or NFS. It's not that you are mounting it into. So that's the reason why I'm a little bit careful with the terminology.
I was wondering how important is it for the interconnections? So for example, this object storage can be distributed in all kinds of places. And then a user, let's say that I want to use it. And so I am sitting here with some internet speed. I need to upload some data that I will analyze there and then download it back. So how can you explain what are the different steps and what kinds of networks it will use?
So let me start with the like everything else we do, we will use with whatever network is there, and at the capacity, the speed, the latency of whatever exists. And part of the work that we do in Pelican, we just got funding to work on it for 4 years. And to give you a feeling, at an investment of $1.5 million a year, which is, let's say, is 7-8 FTEs in American cost, is to deal with challenges in the network and in the I/O capacity of the different players. And sometimes the network is the challenge, and sometimes you know that throughput computing workloads are known to take down the file system of HPC. You know, if you, in the old days, you submitted a large number of blast jobs, they took down the file system because the HPC system doesn't like to have 10,000 or 20,000 processes. Each of them is doing their own I/O to a random place and all that kind of thing. Everyone is now in a lockstep in doing the I/O. So the challenges that we face is what happens if 10,000 jobs want to start and they all want their containers. And they are all independent because it's not that they're running as part of a single application. So we use what is there because if you look at the OS pool, we land at an institution somewhere, and this job needs data that via the OSDF that is sitting in an origin somewhere else. So our job is to bring them together by hook or by crook. So that is, now the steps are that at the moment, we will move data to the compute only from a staging. So the data will have to go from the origin to the staging, and then to the compute. But the idea is that it will be reused, so it is at the staging, and you don't have to go back. So that's the basic philosophy. And I'll be happy to talk to you more, indirectly.
We can discuss on the T also.
And we can always do it virtually.
Another quick question.
Yeah, just running out of time. The next speakers are already waiting in the queue there. So I'm sorry to cut short the question answer session. We can continue with on the T.
Yeah, okay.
Okay. I request everyone. So please congratulate and thank you, Professor, for giving a talk and engaging us for this thing. Thank you, Professor Miron.